Hi everybody, I hope you're all doing well. So where we left off was we have 4 of these little TO5 transistors, and if you take the heat sink off of them, see if I can do that, this is what they look like. And when you look at the bottom, there's a tab on there. That tab represents the emitter. So this pin is the emitter, the center pin is the base. And just like on the big TO3 case transistors, you know, the ones like this, the pin that's connected directly to the case is your collector. So you have emitter, base, collector. Now, the problem is these are hard to find. You know, you can easily find an ECG 128 or NTE 128 and NTE 129, the pairs, but those are relatively low voltage, and most of the amplifiers that use these from back in the day, such as the phase linear that we're working on, they require a special version of transistor like this, and these guys can go up to 200 or 300 volts. They're not real easy to find today. So the only way you can get around that problem is to use a transistor in a different case. That's where you run into trouble. The problem with these is the base is in the middle pin, and they're shaped like a triangle. See that? So they're in kind of a triangle shape. And all of the transistors that are suitable replacements to these and can handle the wattage of these and so forth are in these square cases. And unfortunately, the center pin is the collector on these. So it goes emitter, collector, base, whereas these go collector, base, emitter. And in order to get them to fit, you can imagine you have to twist pins around one another to get them to fit properly. The other thing is they're kind of not, the way they're drilled on the board, you can't get this at the right angle even if you twist pins around. It's just really awkward. So what we have to do is you have to adapt them somehow. And what I've come up with is these little tiny circuit boards. They're really small. And it's nice because you can convert this type of transistor pin out to this type, and you can swap them around. So if you have this kind of a transistor and you have some of these older ones that you want to use that may have better specifications or something, either way you can adapt them. So really how it works is you put 3 pins in here for the emitter, collector, and base. I don't know if you can see that. It's probably going out of focus. And then this just plugs right into it. So I can go just like so, like that, and then have 3 pins come out the bottom. And then this will just plug into where the original transistor went. So when you're done, the modules look something like this. Now this is one with a heat sink on it, and these are pretty substantial little heat sinks. They're 87 cents a piece. You can buy them at DigiKey, and if you go back to the last video, I actually put the part number for this, that you can order these if you want to buy these. So these were really easy to make. There's not much to them, and they were very inexpensive. So what I'm going to do is I'm going to take these modules, I'm going to put them on the board, and I'll show you up here. So there's the original ones, how they were in there. And the new one will just plug right in like this. You might have to bend the pins over a little bit, but they fit, you know, kind of like that. And there you have it. So let me get the amp back out and apart, and I'm going to install those new transistors, and we're ready to test this thing out. So in case any of you are wondering, for the NPN transistors, I am using a KSC3503. I don't know if you can see that on there. And for the PNP transistors, I am using a KSA1381. Believe it or not, these will match up really well with these. So all we have to do is take them out, put the new ones in, and they drop right in place, and this amp's ready to go. Now, these 2 resistors here are much larger than the originals that were in there, because the original ones, which were these little 7500 ohm, you see how much smaller they were? these would have fit a lot better, but I didn't have any of these in that. These were reading really high. Both of them were. They were bad. They needed to be replaced. These were reading over 8,000 ohms, like 8,200 ohms each. So they needed to be replaced. So all I'm going to do is bend this over here, and because these don't get hot, they're so much larger. These are 7 watt. The other ones were, I think, 1 watt. So these are not even going to get remotely warm at all because of their size. And they fit. I didn't have to re-drill anything. They went right in there. So I'm just going to bend these over a little bit to give us a little more space, and everything should be drop-in replacement. Well, there we are, all put together. So the only thing left to do is to power this up. Now, I have not powered this up since we put everything together. The only power that I've done to it was the power supply when it was disconnected from everything. Everything is now completely assembled. I looked over it as best I could. Hopefully I didn't miss anything. We do have a current limiting bulb in there. We always do when we test something like this, but I guess nothing's left but to turn it on and see. So here goes nothing. Matter of fact, let's get you in a different scene here so you could see the bulb. So we're going to use this bulb up here, the big one. Here we go. Good. How about it? Okay, it's looking like we have DC on there because this thing is flashing. Can you see it down there? Right here. I believe that means it's in protect. So let me get the meter out, and I will see if we have voltage where we're not supposed to be having it. What do you think? So let me go to the ground here. Now let's go to one of the speaker terminals, which would be right here. Oh yeah, full voltage on that side. So something is not right. Something is very, very unhappy. So we're going to have to do some, let's see if both channels are doing that. Let me go to the ground. Let me go to the other side here. Starting to smell something. This one does not have anything on it, so I'm going to shut this off. Nothing, the bulb is completely dim, so it's not drawing current. But I don't feel anything heating up. No heat there. No heat there. I mean, these are just barely warm. And the transistors, the drivers at least, are ice cold. So it may be that one of the biases is off or something, but let me take a couple measurements and then I'll be back when I find something. Okay, hopefully I will remember this where I leave off, because I'm going to have to leave now, but I think I found something. And that is on both sides. I mean, one side's worse than the other, but on both sides I have a DC offset right here on pin 6. There's zero signal on pins 2 and 3 of these op amps, but there's a very definite signal here. Now you can see there's a path. You have your negative 90 volts or 100 volts, whatever it is, coming in, and it goes through these two diodes. This is your negative, and this resistor. They're in parallel. These diodes kind of clamp this off at 2 voltage drops. And from ground through a 1.5K resistor, and then through this and down here. Now, none of this can do anything if there's no base voltage. But the fact that I have base voltage and I have no voltage here and here tells me that that base voltage will probably be there even with this chip out. So I'm going to remove these chips. I'm going to look on pin 6 with no chip in there and see if I still have that in there, then these transistors are leaky. even though they tested good with the diode check, they're leaky. So let me shut this off and bleed it down, and I'm going to pull those chips. Okay, turning power back on. Go back on pin 6 here. And now we only have 0.2 of a volt. If I go on pin 6 here, I have 300 millivolts. There really shouldn't be anything there. Well, now it's 100 millivolts, jumping around. Now it's down to nothing. So something is going on when we put these chips in. Now, one thing I am wondering is if this thing is going into oscillation. And that could be, because if you remember, turn this off. If you remember, I added this to keep it from oscillating, but maybe on this amp it doesn't like it. I don't know. So I'm going to check that. I'm going to use a scope and see where we are, and if it's oscillating, then we'll know where our problem is, and that would be my fault. Okay, I have this hooked up here. I'm going to turn it back on. Oh boy, there's your problem. We are oscillating at 7.4 kilohertz, and I'm at 10 volts per division. So 10, 20, about 25 volts peak to peak. So I'm basically going rail to rail on that. Turn that off. And yeah, so I have a 7.4 kilohertz oscillator. Let's go on the other channel. I bet it's doing something crazy too. Okay, channel 2, power on. Well, it's not quite as bad now, is it? It's doing something wackadoodle also. It's got offset. Ain't that beautiful looking, huh? Let's see if I can get the trigger on that. That's also 7.4 kilohertz, but it's also got negative offset to it. And it's only at 2 volts per division, and it's really warbly. So, yeah. These things are oscillating, and I'm going to remove those. I'm going to remove this. Where are we at? There. I am going to remove this and see if it makes any difference whatsoever. Okay, I snipped those little capacitors out of there. Let's turn this thing on. Well, that's better. I don't have a big old square wave now, but there's still noise galore on there, isn't there? Now that could possibly be because I don't have anything. I have the fuses pulled from the output section. So there's no negative feedback loop because you don't have any voltage in the outputs, but I don't know. So I have to leave now, so I will come back to this. But I just wanted to leave it here so I remember where I was. Okay, it is the next day, and first off, the noise that we were seeing after we removed those 2 little capacitors was not oscillation. It was actually noise because the input volume pots were turned up and everything's sitting out in the open, and it was picking up actual noise, and we were seeing that noise. So after turning those down, the level knobs down, that flattened out. However, still have DC offset on one channel, not the other. The other channel seems to be okay. So I went through and looked, and the voltage that's showing up at this point is positive voltage. It's really important to look at the polarity of the offset. If it's positive offset, that means this row up here is what's leaking voltage. If it was a negative voltage here, then I'd be looking down here. So the first thing we want to look at is our drivers and so forth. These all seemed to check out okay. So I came back here to my new transistor I just put in, and this is the NPN. So that would be from, I would put the base on the positive lead. And if I go from base to emitter to check our VBE, if I can get on it, hold on a second. This is awkward through the camera. You can see it reads a forward voltage drop. But if I go from base to collector, see if I can get on it, I have a dead short. This transistor shorted. Now I don't know why. It may have been a defective transistor right out of the box, but I believe I tested these before I put them in, but who knows. So I'm going to take this transistor out and get it replaced, and then we'll see if that's all that was wrong. And we're going to go back one step too, and we're also going to check the pre-drivers going into that, which is up in here. I don't think any of this is going to be bad, because when you get back behind here, you're actually looking at your Class A stage. And I don't think, your voltage amplification stage, and I don't think that's going to be a problem there, but who knows. We'll replace this first, and then we'll see what it looks like. Okay, as it turns out, this transistor was not bad. And all that was wrong was this little capacitor, this anti-oscillation capacitor. I don't really want to call it a Miller capacitor, but it kind of negates the effects of the Miller effect to prevent oscillation. Anyway, this was a component that was put on there by Phase Linear. It was added after the fact later on, so this is a later revision. And I noticed when I looked at the schematic, it actually is not in here. It goes between the base and the collector. And you can see there is no collector to base capacitor here or down here. They only put it on the positive side for some reason on both channels. So I kept that. The original one that was on there was a ceramic like this. I just went to these little tiny ones. They were a little easier to put on the board, but this one got a little bit too close for comfort with those tracks, and I think I had shorted a couple tracks out with that, and that's why this was reading shorted from here to here. And sure enough, if I check this now, back off, there are no more shorts. You can see no shorts. And if I go to diode check and I put my positive lead here because it's a NPN, you can see going in this direction I have a voltage drop, and going in this direction I have a voltage drop. So the transistor is good now. So that again was my fault. So 2 Tony errors. But of course you have to remember I rebuilt this entire thing. So you're going to have mistakes here and there, and I just want to show them to you and how to deal with them. Don't panic if something doesn't work. You can fix it. You just have to kind of go through and look at the symptoms and trace it back from there. So anyway, that's where we are right now. And I think now we should be able to have both channels come up like they're supposed to. So let me get things connected back up, and we'll see if our DC offset has disappeared. Whoever has the most meters wins. All right, so I'm hooked back up. Let's turn this thing on, and hopefully this meter will stay near 0 volts. Here we go. Yes! So let's see if the flashing light in the corner of the screen goes solid. It did. Excellent. So there's a teeny little bit of offset there, but I think part of that might have to do with our bias. So let's go, I'm going to move these meters over to the bias resistors, and we're going to check bias on both sides. Okay, let's turn this thing on. And we're looking for about 340 millivolts, 350 millivolts. That's a little bit high right there. So let's turn that down. Well, I don't know why one's reading positive and one's reading negative. That's really bizarre. But let's see what happens if I go like this. If it flips around the other side, I doubt it. No. doesn't. That's odd. Okay, so let's go for about 350. I'm gonna have to look into why that is. Why one side is reading. It may be because of the resistor I'm reading across. I think that's what it is. I'm across one side on one and the other side. Now I understand. Dummy. So you can read across this one or this one. So on one channel I'm hooked across this resistor, on the other channel I'm hooked across this. That's why I'm getting a positive versus a negative voltage. This is close enough. It just has to be somewhere between, let's say, 350 to 400 millivolts. So we're good. I think we're ready to test this thing out. See if it'll pass a signal. One more little note is you want to do the final bias adjustment after the amplifier has been warmed up. They say wait 5 minutes. I say leave it about 10 minutes. And even after that, run the amp for a little bit and test it and kind of see where you are again. And if it moves, readjust it again, you know, after it settles, after you've been running it for a little while. It's not super critical on this amp. You just want it to be, again, right at conduction. You just don't want it to be too high, because if the bias current is too high, all it's going to do is make the heat sinks run hot, even when it's sitting idle. We don't want that. So let's hook up to our speaker terminals and let's put a signal in there and let's see what happens. Okay, I'm not sure where I left off here, but now I'm on the other side of this surgery and I've lost some of my voice here, but I'm ready to put a load on this thing and try it and see what happens. Everything seems to be working now. After I found that, removed those capacitors at the front end here. So I removed, where are we? That one that went through here, and you can see this is an updated schematic, which I will post on this video so you can, again, screen capture it. And so now this is what we have. The let's see what else. I added this up here onto the schematic. This was factory. It just wasn't in the schematic. It was something they added later on, apparently. So let's see if this thing will work with a load on it right now. So I have, let's see here, let's put 1 kilohertz. Hold on a second. I have 1 kilohertz, and I probably should turn the amp on. And I'm not going to put a real big signal through it because we're still using the a 300 watt current limiting bulb in here, because in case something goes wrong. You know, we've done a lot of work to this thing. But you can hear the relay just kicked in, so we're out of protect. I'm going to go up here onto the scope and let's turn this on. And let's set this. Okay, and there are the 2 channels. So blue is the right channel, yellow is the left channel, and you can see how pretty close they are on top of one another. And right now, we're only looking at about 3.4 volts RMS, which is, you know, not a whole lot of power. So we're just a little under 1.5 watts. And even with just 1.5 watts per channel, you could see it starts lighting the bulb up. So that's going to cause a little bit of distortion in there. You can kind of see where it fringes a little bit, but that's okay. What I want to do now is just take a couple of samples at different frequencies and see where we are. So I'm going to go over to the amplitude. I'm just going to lower this right there. And let's get our trigger in a reasonable place. And you can see I'm just going 2 divisions above and 2 divisions below. So it's about 2 3/4 volts RMS. And then I'm going to just go change the frequency now. So I want to go down to, let's say, 100 hertz. I got to readjust the scope. And it's flat. All right, so let's go down to 50 hertz. And again, nice and flat. And let's go 40, 30, it's starting to roll off. 20, now it's really rolling off. 10, major roll off. So, yeah, just a tiny little bit down at 20 hertz. Let's see, there's 20. And we're down to just a little bit under. So we could trim that up a little bit. You know I like bass. And if we adjust the feedback resistor a little bit on that inline filter, we may be able to get it to be flat all the way down to 20 hertz and start rolling off. But let's go up in frequency now. 10 kilohertz. Nice and flat. And let's look at 20 kilohertz. Nice and flat. Let's go back to 1 kilohertz. And I'm going to check my heat sinks. And they are ice cold. Not even warm. This is good. They shouldn't be with that low of power. And let's go to a square wave now and see what happens if this thing oscillates. Nothing at all. Perfectly flat. I like that. Okay, so our trigger's set in the middle. Let's try to stretch this out and see what kind of rise time we're getting. Of course, I can't check the rise time and everything. It's not going to matter until we get this thing closer to its full power. So really, to check the slew rate of the amp, we have to kind of be able to drive it hard without the current limiting bulb. So we'll wait on that test till we can kind of get this in a trustworthy manner. But right now, I just want to run this amp for a little while and just make sure, and it's going to stay on its current limiting bulb. And I'm going to just make sure nothing overheats, make sure everything's working properly, and then when we come back, we'll let it off the leash and see what happens. All right, so it's another day, and I can only be down here a little bit at a time, and I start to get sore. I have to go back up and lay down with an ice pack, but thought I'd come down this evening and make a couple more little tweaks to this. I've been thinking about it a lot, and I'll show you what I did. A couple of things that I'm finding out. Number one, I was thinking of substituting the TL072 with an OPA 134. That turned out to not work because the 134 requires, I believe, more current than the 072. And what was happening was the thing was just driving to one rail. Now, I'm sure I could play around, with the power supply and everything and get it to balance out, but it was not happy. So we're going to stick with the TL071 right now. A couple other things I changed. In this limiter circuit, as I said, if this thing goes to the rail, this will protect it so you won't blow your speakers, but you're going to put that whole almost 100 volts, in the 90 some volts through this 180 ohm resistor, through this 3.9K, through this little 1N4148 diode to ground. So what did I do? Well, I changed these out. I changed this to 180 ohm metal film 1 watt resistor. I changed this to a 3.9K 2 watt metal film resistor. And I changed these to UF 4004. UF stands for ultra fast. So these are similar to a 1N, but they're actually ultra fast diodes, very similar to a 1N4148. And they'll work just fine in this circuit. Now you might say, well, these are designed to open up. Well, really, I don't want these to open. I want them to kind of hold where they are. And I just need this. It's still going to get really hot unless you put like a 5-watt resistor in there. But I just need it to hold long enough to realize something's wrong so I can power it off. So we're just trying to make this amp more reliable and kind of think about ways in which this amplifier fails and try to kind of preempt that. We want to control the failure of this amp if it fails and do the least amount of damage to the circuit as possible. So that's what all this is all about. So now I have everything in there, and you can see the UF4004s. You can see the larger 2 resistors here, and same thing on this side. The other thing I did was the negative feedback circuit. This resistor for this filter circuit here, I changed it from a 270 ohm to a 750. If it was 810 ohms, it would be perfectly kind of rolling off at 20 hertz. But as it is right now, I didn't have an 810. The closest I had was an 820, and I didn't really want to go that far. I kind of like just a slight drop at 20 hertz that we're getting right now. What this is going to do is, it's really, the way this amp I think was originally designed was they had it start to roll off at about 40 hertz, and not harsh, but by the time you were to 20 hertz, it was a pretty decent roll off. And it's because this is a very high powered amplifier. And I think the whole purpose of this was to be able to conserve some of the power. Instead of losing power in the subsonic range, you wanted to direct it towards the more audible bass notes and use that power. So if you're driving a big set of speakers for huge amounts of volume, this amp would be more efficient towards that. By making that change, what we're doing is we're refining this a little more for listening to it like in a home listening environment. Yes, it's still 350 watts, but when you're driving subsonics or driving down in that 20 hertz range, that eats up an awful lot of that 350 watts. And so we don't care about that because we don't need that much volume. What we really want is clarity, a lot of clarity and a lot of dynamic power, even at lower volumes. And that's going to help us with that. So that's why I made that change. And it's an easy change to put back to factory original by just removing these 2 resistors down here, which would be this green one and this green one right here. See the little one green resistor here and one here, and just swapping it back out. Now the other thing, these 2 resistors here were replaced. One of them was replaced anyway. You could see I took the 2 out. You could see they're different. This is the one that belongs in there. This is the one they had on the one channel. So I think these failed along with these 3.9Ks. And again, they're going to fail. If one side goes to the DC rail, you're dumping the whole DC rail across those resistors. So hopefully that's going to make things more reliable if you can follow along with that. So let's see what kind of improvement we've made and see if this thing works. It's now connected to an 8 ohm dummy load. And I'm going to put it up here. And let me get you lined up. Okay, let's turn it on. And right now we're at 1 kilohertz. And you can see I'm only driving 3 watts or something like that in there, just a couple of watts. They're overlapping pretty well. And so what I want to do now is you can see where we are. We're touching 2 gradicules above the center and 2 below. So let's go down to 40 hertz where we were before, and it should still be flat. And it is. See there? So there's almost no drop off at all, just the tiniest amount. Let's go down to 30 hertz. And you can see now it's not really rolling off at all. And then when we get to 20, you see that slight roll off now. That's where it starts to roll. And if we go to 10 hertz, now you have roll off. But there's still a good bit there. That's what we want. I want to have that deep bass and the ability to carry it through. Now, again, if I went and put that 810 ohm resistor, if I had one, or an 820, which I did have, that would change that roll off even a little bit more. If we go up to high frequency, I don't know, let's go all the way to 20 kilohertz. You can see it's really nice. And it rolls off just slightly there too. See that? And if I go to 10 kilohertz, it's right there. See that? So basically what you're seeing is that at the two ends of the spectrum, you're getting your little bit of roll off. And that's good. That's kind of what I want. And it's also kind of controlling this amp that has a tendency to oscillate if you're not careful. So that's going to kind of keep the real high frequency and low frequency components out of the amp. So this looks good, and I think I'm ready to put it all together to do the final testing on it. And then this thing will be done, and I'll have to get somebody to lift it off the bench for me because I can't really move it. But we'll do a couple more tests, and then maybe we'll test it more thoroughly when I get better, and we'll put it through its paces. But I have a few other ideas for videos I want to do in the meantime, so I'll get this cleared off after this video. Okay, I have this thing put together, and you can see I have all the wires hooked up here, and I have the distortion analyzer hooked up to this channel here, to the right channel. And I want to put a 1 kilohertz signal on there and kind of show you a couple things. So here's 1 kilohertz, and remember we set the bias on the amplifier according to the instructions. They want that 30 to 40 or 300 to 400 millivolts across that 10 ohm resistor on the driver. You see, you have a pretty nice looking sine wave there. It looks pretty clear. The fuzziness is the digital scope, okay? But if we go over to the distortion meter, it's really ugly. You can see I only have 60 millivolts driving into the amplifier, and the output's very small. I'm only outputting about 500 millivolts, so it's very low signal. But look how bad the distortion is. It's 0.27% almost. So what I'm going to do is I'm going to show you down here. If you look straight down, I don't know if we can catch this or not. See if we can get this in shot. You see this adjustment right here? Right here, the pot? I'm going to adjust that. And watch what happens to the distortion. So here we go. Okay, so I'm going to lock the camera on here. And now I'm going to adjust this pot. Remember, it's set to factory settings for the bias. So let's go. What's happening? And there we go. And it bottoms out at around 9 or 10%, 0.01 or 0.009%. You're getting really into the bottom of what this, the sensitivity of our test equipment. Okay, now let's move it up to 10 kilohertz. Let it settle. Look at that, even better. And we'll go to a low frequency. Let it settle. And we're down in that 20 hertz range, and it does get a little bit more distortion at the low end. And that's just the way this thing is. Again, I'm very, very low signal, and this is because this crossover distortion thing has its greatest effect at, at very low volumes. So that's what's going on. Okay, this amp's working very well, but one problem, and that is when I have the distortion set the same between two channels, this channel is absolutely perfect. It's flawless. Runs really cool, perfectly. This one runs hot. I mean, not hot like burn your hand, but I can physically feel how warm this side is getting versus this side. So there's something wrong with one of the transistors in here, because when the bias is set where you have the lowest distortion, you're actually turning these transistors on too hard, and you got a lot of idle current that's causing this thing to overheat. So we probably have a bad transistor somewhere. So this is where we're going to leave it for right now, because I'm really starting to get pretty sore here. So I'm going to have to go up and sit down and put some ice on. And when we come back, I'll take a look at this and find out why this side is getting hot. Okay, so I solved the problem with this channel idling warmer than this channel. And all it really was when I checked across, let me see here where I am. When I checked across this 10 ohm resistor right here, I noticed that the bias was only about 50 millivolts higher on the left channel than it was on the right channel. I barely just adjusted the bias control. It brought that right down to about the same level as the other channel. And by the way, where they settled in for the lowest distortion was closer to 500 millivolts instead of 400 millivolts. So yes, we have to idle this a little bit hotter because of these transistors and everything to get the low distortion. But by just reducing it that little amount, these are now running, I mean, they're identical. I mean, at least by feel. So that's all that was. Now, we're going to drive this close to its maximum power. So for 360 watts, you're going to want somewhere around 53 volts RMS into that 8 ohm load. So let's see if we have that. I got it dialed in pretty close. As you can see, there's 46, so let's go up just a little bit. Let's try it again. A little more. 53.5, okay. I don't want to just heat this up because it's sitting, doesn't have good airflow around it because it's sitting on the bench directly. And let's look at what our distortion's doing. That's what I like. Perfect. And of course, I blew the fuse on that last run, and this is the main fuse for the mains incoming. And the reason for that is the original configuration of this amp when it came onto the bench, if you recall, was for 240 volt mains, and I rewired it for 120, but I didn't replace the mains fuse. When you run the amplifier on lower voltage, of course it's going to draw higher current. So the recommended fuse for operating in 120 volt mains is going to be a 10 amp AGC 10 amp fuse, and this one had a 7 amp, which is the wrong one to begin with because it should be a 5 amp for 240 volts they're asking for. But nevertheless, you can see it didn't cremate the fuse, it just opened it because it overheated. So I will put the proper fuse in there. This thing draws an awful lot of current, of course, when it's running at its maximum output. Okay, so I'm going to use a proper 10 amp 250 volt fuse, and I'm going to use a ceramic that has the sand in it. The reason being is when these fuses open, they open more quickly. In other words, they don't have that problem where when they explode, you'll get that splattering, that, you know, it'll quench it more so that you don't have that extra flashover that happens when a glass fuse opens up. So these will actually break the current much faster than just a straight glass one. It's a little added safety on there. These are more expensive, but they're worth it if something goes wrong. You got a little better chance of not trashing other things. All right. Okay, I'm not going to run this too long on the bench, but clipping is taking place at about 59 volts, we'll call. That's going to give us about 435 watts per channel. And that's both channels driven. So I would say that's well within spec. Now, if you notice, there was a little bit of ringing when we hit oscillation, and that has to do with, with the transistors. But it was not out of control, and it didn't seem to be too bad. Everything is working totally as expected on this amp, except for one thing. and I think I know why. According to the service manual, let me see if I can get this. When we look at the specs, the input sensitivity of this amplifier, you're supposed to have about 1.2 volts RMS to get your full 360 watts of output. Now, using my signal generator, and again, you have to understand the loading of the signal generator, I'm currently using about between 4 and 4.2 volts RMS, which is way more than this, almost 4 times what it should be. Now, part of this is because of my little splitter network and the input circuit that this is going through, all of these, because it forms a voltage divider. You have to understand that. So that's going to account for a little bit of that. My output on my signal generator is an output into high impedance, so that's not really correct. So it's really not putting 4.5 volts RMS. It's less than that, but nevertheless, it's still a little bit lower, or still a little bit higher input sensitivity than it should be. But I think right now what I'm going to do is, we have a generally working amplifier. I really can't do any more lifting and can't stay at the bench very long. So what I'm going to do is I'm going to edit this video. That'll give me a little more time. I'll spend a day or so editing and posting the video. And then I'll come back down here. We'll make our final tweaks to here. And then that'll be the end of it. And that should be a short video at the end, because we'll just do a couple more tests. We'll do a listening test. You know, I'll play it into the microphones. I know a lot of you like that. And then we'll do our final draft of this that we'll post up for all of you to copy and paste if you want. I want to address one comment. Somebody said I'm wasting time and effort and money by not buying the white oak upgrade boards. And I responded a very short response to that, because I thought I needed to respond to that. And my thoughts on it is that you expend a lot of time, effort, and money to purchase and install the white oak boards. So I'm not really saving anything there now, am I? And to me, the greater poverty is passing up an opportunity to learn. That's what this is for me. Anybody can buy a board and plug it in, but not a lot of us can go through all of this and kind of learn as we go. We make mistakes along the way, and you saw me make plenty of them during this video, and that's all right. That's how you learn, you know? And I encourage all of you to step out of that comfort zone and get rid of that mentality of, well, it's just stupid to waste your time on something that somebody already knows. Well, if we all thought that way, how would anything new or innovative come out in the future? So you young folks especially, don't listen to people like that. Always be willing to do the extra work for yourself and to learn. It's a great feeling when you figure it out and you understand it at that level. So I'm just going to step off my soapbox now. And as always, I'm going to wish you all peace, joy, happiness, and good health in your lives. And we'll be back real soon. Take care, everybody. Bye-bye.